Section 5.8, Coordinate Proofs. Example 1, in the diagram, rectangle KLMN is centered at the origin, right here, with sides parallel to the axes. So this side's parallel to the x-axis, same with the side LM and KN are parallel to the y-axis. Find the missing coordinates. So we're given the coordinates for point L. We need to find the coordinates for M, N, and K. Now let me pause right there. Notice that the coordinates for L are variables. That's what's going to make these actual proofs and not examples. The difference between an example, which would say maybe this was 2, 5 or something like that. If this were an example, then that would only show that whatever it is that we're trying to prove later on down the line would only be true for that specific square or rectangle or whatever shape that you are working with. Making these variables, but variables with restrictions. For example, if this is A, B, and this needs to be a rectangle, then M, the x-coordinate for M, has to be A as well, because L and M are the same distance away from the y-axis. So they're both A, something. Now, M has to be the same distance below the x-axis as L is above the y-axis. So if L is B units above the x-axis, then M is B units below the x-axis, making it negative B. So there's our coordinates for point M. So yes, these are variables, but they're variables with restrictions. Now I'm going to continue going around. We'll do K next. So K is the same distance to the left of the y-axis as L is to the right of the y-axis. So L is A units to the right of the y-axis. K units is A units to the left of the y-axis, or in the negative direction, making it negative A units. The x-coordinate is negative A. The y for L and K are the same. They're both the same height above the x-axis in both cases. So they are both B units above the x-axis. N is actually easy to figure out because N is the same distance to the left of the x-axis of the y-axis as K is, and it's the same distance below the x-axis as M is. So we take the x-coordinate from K and the y-coordinate from M to get coordinates for N, negative A, negative B, which makes sense because we are in the third quadrant here for N, and everything's negative. X and Y are both negative in the third quadrant. So all of these have variables for their coordinates, but they're variables with the restrictions, which I said before. What do I mean by that? I mean the restrictions force this shape, KLMN, has to be a rectangle no matter what A and B are. If A is 5 and B is 7, then this is going to be 5, negative 7, negative 5, negative 7, negative 5, 7, and the result will be a rectangle. Has to be. We're going to have parallel sides being opposite. We're going to have right angles. We have perpendiculars. So it has to be a rectangle, even though these are variables for coordinates. So in this unit, as we go through, and we're using these variables to do these problems, they're going to be actual proofs, because this KLMN rectangle can be any rectangle. Or another way of thinking of it is all rectangles. So if I prove something true for this rectangle, it's true for all rectangles, because KLMN can be any rectangle, because A and B can be any two numbers. Alright, example 2. Use the properties of parallelogram to find the missing coordinates. Do not use any new variables. So we are told that this is negative x. We are told that this is negative p, q. O is very simple. That's the origin. That's 0, 0. Those are the coordinates for O. All right. If C is x units to the left, actually we have this other part here. This is an easy one. The y coordinate for C is 0. So we end up with negative x, comma, 0 for C. And yeah, we're allowed to use zeros. The origin is a convenient place to put a vertex of a shape. So 0, 0, negative x, comma 0. Now, C is negative x units in the negative, is x units in the negative direction away from the y-axis. A is p units away from the y-axis in the negative direction. B is going to be C units, because this AB is parallelogram, so AB has to be the same length as CO, right? OC and AB have to be congruent. So if they're congruent, then from A to B has to be X units long, just like from O to C is X units long. Since this is X units long and this is X units long, we know the length of AB is X units long. The length from the y-axis to A is P units long. So from the y-axis to B is a combination of X units and P units. P units plus X units. But we're going in the negative direction. So it's negative X minus P, comma. The y-axis, the y-coordinate is actually really easy because it's the same height as A. We need AB to be parallel to CO. CO is horizontal, it's got a slope of 0. So AB has to be horizontal, it has to have a slope of 0, which means Q is our y-coordinate. And there are the coordinates for B, the missing coordinate for C, and of course the missing coordinates for O, which were super easy. Okay? It is often convenient to use coordinates that are multiplied by 2. This comes up and makes things easier if we're dealing with things that involve midpoints. The next example is going to use multiples of 2 to avoid fractions. They're still variables. All right. I mean, I could have called this negative 2p, comma 2q. I could have called this negative 2p, comma 3q. And this can still be any parallelogram as long as I fit the other coordinates to scale, right? This would still be negative x, comma 0. This would be negative x minus 2p, comma 3q. And it would still be a parallelogram. And maybe that makes the arithmetic, the algebra later on, easier. Okay? For example, here we have this triangle, but really we're just looking at this segment RP, right? And we want M to be the midpoint of RP. So what are the coordinates of M going to be? Well, the coordinates for R are 0, 2b. So we've gone up 2b units. And the coordinates for P are 2a, 0. We've gone to the right 2a units, which means M is going to be halfway to P and halfway to R. So, well, halfway to P is a, 0. Halfway to R is 0, b, making the coordinates for M a, b. And we avoided fractions. The advantage of thinking ahead when picking our variables to make the arithmetic a little bit easier. And again, if you want to use the midpoint formula, you're going to get the exact same answer. The midpoint formula is really just the average of the x's, so 0 plus 2a divided by 2, and the average of the y's, 0 plus 2b divided by 2, and you get a, b again. All right. So they're convenient choices. If you have right angles, I'm not going to read all of this. What I want to summarize is that this basically says where you put an object, and these are examples, where you put an object on the coordinate plane can make the problem easier. It might be more convenient to have the coordinates of one of the vertices be on the y-axis and two of the vertices be on the x-axis. It might be more convenient to have one of the vertices be at the origin and one of the vertices on the x-axis and the third vertice somewhere out here, random. It may be convenient to set up an isosceles triangle where you have O, D are, so O is at the origin, D is here on the x-axis with coordinates negative 2a, 0, and then C would have to be A, comma, whatever you choose for the y coordinate. Now, chose B, but it could be any variable because it can be at any height. Okay, it might be more convenient to put the vertex of the isosceles triangle on the y-axis and the base angles along the x-axis, positive and negative. I don't know. It all depends on what it is that you're trying to prove. So these are all different possible places that you can put different shapes to make them a little bit easier to solve whatever problem it is you're trying to prove. All right, so place each figure in the coordinate plane in a way that is convenient for finding side lengths. Assign coordinates to each vertex. So we have a scalene right triangle. So if we're going to do a scalene right triangle, I want it to be, I have to make sure that it's going to be a right angle. Well, do I have any right angles anywhere on the coordinate plane already? Yep. The origin right here, the x and the y axes, form a right angle. So that's a convenient one already. And let's say we're going to put one of the vertexes here and the other vertex up here. Okay, so if I call this, so we've got 0, 0 for the origin. Over here we've got something, comma, 0. Pick a variable. A. Up here we have 0, comma, something. Now I'm going to pick a different variable other than A because I want this to be scalene. B. The only caveat is we don't want A and B to equal each other. So A does not equal B. That way it's guaranteed to be scalene. If A and B are the same, then it wouldn't be scalene. It'd end up being isosceles. Okay. Part B. Find an isosceles trapezoid. Find a better placement than on the previous page. Well, what did we have for an isosceles trapezoid on the previous page? So we have this one here is an isosceles trapezoid. Actually, this is not bad. This is usable. Okay, we could have an A, a B, a C, and we'd have to figure out the coordinates for W, right? A minus B, comma C. Give myself a little bit more space. A minus B, comma C. And that works. There's nothing wrong with that. But I think we can do better. I want to make this an isosceles trapezoid. I'm actually going to center it on the y-axis. So I'm going to make the y-axis an axis of symmetry for this trapezoid. So I'm going to do 3, 3, right? 1, 2, 3, 1, 2, 3. And let's do 5. 5, 5. Oops. Now, we're going to need some variables here, and some of these are easy to pick. Let's go A, comma, 0. Okay. Well, if this is A, comma, 0, I'm forced now here for the coordinates over here. I don't have a choice. I need this to be an isosceles trapezoid. Coordinates here are going to have to be negative A, comma, 0. If I'm making the y-axis an axis of symmetry, I don't have a choice. That has to be A and negative A. Okay? This is going to be a different distance. Probably shorter, but it doesn't have to be. This could actually end up being wider, and this could be the shorter part. It could be a flipped over trapezoid. But it's different than A. So B. it's some height above the x-axis. I don't know what that height is, it's a variable. C. Now I'm locked into what the coordinates have to be here. I don't have a choice. Negative b, comma, c. And again, so that this is a trapezoid and not not a rectangle or a square by accident, A can't equal B. It can equal C. B can equal C. That could be all right. I could have 3, 3 could be a coordinate. I could have the distance from here to here be the same as the height from here to here. In fact, it is in this. This is 5, this is 5, if I count those as 1 units. So A could be equal C, B can equal C, but A really can't equal B, otherwise we're not going to have a trapezoid. Okay. Example 5, we're going to write a proof that uses side angle side. The coordinates of triangle POS and ROS are given. We want to prove that SO bisects angle PSR. Okay, that's our goal, is to prove that SO is bisecting angle PSR. So what do I know? What do I know about triangle POS and ROS? Well, we're going to have to prove that they're congruent, because then we're going to prove that this angle and this angle are congruent to each other. If they're congruent to each other, then SO is bisecting angle PSR. Okay? And that's what our goal is going to be. Prove these two triangles are congruent by side angle side. There's more than one way to prove these two triangles are congruent, but I'm going to prove them by side angle side. What do we know about line PR, or the x-axis, and line SO, or the y-axis? What do we know about them? We know they're perpendicular. This slope is undefined, this slope is 0. They are perpendicular. Okay, well, what does that mean? Therefore, angles POS and angle ROS are right angles by the definition of right angles, of perpendicular, sorry, getting ahead of myself, perpendicular. Therefore, angle POS is congruent to angle ROS. All right angles are congruent, or the right angle congruence theorem. Right angle, I forgot the angle symbol. Right angle congruence theorem. What can you tell me about PO or RO? Let's start with RO. We know RO is equal to 3 units. What can you tell me about PO? It's equal to 3 units. Therefore, RO is congruent to PO. Definition of congruent segments. 2 segments that have the same length. What can you tell me about SO? Well, it's 4 units, but it's also congruent to another segment that's 4 units. Yeah, SO. It's congruent to itself. Reflexive property. Therefore, triangle POS is congruent to triangle ROS, side angle side. Angle PSO is congruent to angle RSO, CPCTC. SO, ray SO, bisects angle PSR. Definition of an angle bisector. There's example 5. Example 6. Place an isosceles triangle in the coordinate plane with vertices P is negative 2a comma 0, Q is 0 comma a, and R is 2a comma 0. Find the length of each side, then find the coordinates of the midpoints of each side. So I'm actually going to come over here to, I've got a blank piece of paper over here. Let's make our x and y axes. We have P negative 2a comma 0, Q is 0 comma a, putting it on the y-axis, and what do we have? R is 2a comma 0. Forcing this to be an isosceles triangle, conveniently placed so that it is symmetric on the y-axis. Two of the vertices are on the x-axis, one is on the y-axis. Our goal is to find the length of each side and then find the coordinates of the midpoint of each side. So the length of PR, easy. PR equals 2a plus 2a, 4a units. Okay. The length of, we'll do RQ first. Distance formula if you want, or Pythagorean theorem. Let's do a distance formula. So QR, Pythagorean theorem and the distance formula are exactly the same. QR is square root x2 minus x1 squared plus y2 minus y1 squared. QR. So x2, 2a minus 0, or just 2a squared, plus y2 minus y1, 0 minus a, or negative a squared. Square root is 4a squared plus a squared, and yes, it's plus a squared because that becomes positive. Square root of 5a squared becomes a square root of 5. Technically, that's an absolute value of a. When you take algebra 2, you're going to know that would have to be in an absolute value because even comes out odd. Technically, it's the absolute value of a, but we are using a as positive numbers here, so we're okay with it being just a square root of 5, but we'll call it QR. And don't worry about that on a quiz or test because you haven't taken algebra 2 yet. So if you just write a square root of 5, you're fine. If you write absolute value of a square root of 5, a little bit better, but I wouldn't worry about it. PQ, we're going to do distance formula again. It's going to be exactly the same as QR. Let's do PQ. Square root And I'm going to skip writing the distance formula. I'm going to jump right to here. Negative 2a minus 0 squared plus 0 minus a squared. And I think you should see that it's going to be exactly the same. So we've got negative 2a squared is going to be 4a squared plus negative a squared is a squared. And again, we end up with absolute value of a square root of 5 pq, not rq. pq's length. Okay, we also have to find the midpoints of each side. That's actually easier to do. We can come right up here. Well, midpoint of PR is easy. It's the origin, 0, 0. Midpoint of QR is going to be a comma a over 2, having a fraction. And you can see the advantage of having this be a 2a made this not a fraction, and this disadvantage of this not being a 2b or something made this into a fraction. And over here, coordinates for the midpoint of PQ are going to be negative a comma a over 2. And I think that answers all of example 6. Find the coordinates, midpoints of each side. Yep. Okay, so back here in example 7. Write a coordinate proof. So when it says write a coordinate proof, I know you instantly go to thinking it's got to be a 2-column proof or a paragraph proof or something like that. The truth is, when you're doing a coordinate proof, you're just showing me the algebra. Do whatever algebra you can do to prove what it is that you're trying to prove. So the algebra that you have at your disposal are slopes. If you want to prove lines are parallel or perpendicular, you're going to use slope formula. If you want to do midpoints, you're going to use the midpoint formula. If you want to find the length of something, you're going to use the distance formula. You are doing the algebra to do the proof. All right, so coordinates of the vertices are given. So we have 0, 0, m comma k, m plus h comma k, and h comma 0. And all of these work to make this a parallelogram. It's nice and convenient. This is h units. This is also h units. I don't know the length of this because it's going to be the square root of m squared plus k squared. And this will end up being exactly the same length. So we want to prove that angle TOU, which is this one here, is congruent to angle VUO, this one here. So to do that, I'm going to prove that TO is parallel to UV. Why? Because these are alt-int angles. They make that Z-like shape. When they make that Z-like shape, they are alt-int angles. Alt-int angles are congruent if the lines are parallel. Proving lines are parallel in the coordinate plane is easy because we just got to show that the slopes are the same. So the slope of line segment TO is equal to y2 minus y1 over x2 minus x1, or k minus 0 over m minus 0, or k over m. There's the slope of TO. If the slope of UV is the same as the slope of TO, then we're going to have parallel lines. Slope of UV, again, y2 minus y1, so y2 is k minus 0, k minus 0 over m plus h minus h, m plus h minus h, k over m. Therefore, TO is parallel to UV. And angle TOU is congruent to angle VUO by alt int angles theorem. I didn't have to do a 2-column proof or anything like that. I just did the algebra and drew the conclusions from the algebra. That was example 7. Example 8. As part of a graphic design, you draw a rectangle and then connect the midpoints of the sides. Prove that the quadrilateral MNPQ, the midpoints, formed has 4 congruent sides. We want to prove that it is a rhombus. All right, so to do that, we need to know what the coordinates of these are. So let's go, coordinates for M are 0, A. Coordinates for N are B, 2A, B, 2A. Coordinates for P are 2B, A. And the coordinates for Q are B, 0. Okay, so we've got our coordinates. Now we just need to prove that this is a rhombus. To prove it's a rhombus, we're going to need to do distance formula 4 times. We need to prove that we have 4 congruent sides, so we're going to do the distance formula 4 times. I should have enough room to do it here. I thought I might have to grab the blank paper, but I'm going to save the blank paper for example 9 if I need it. I'm not even sure if I'm going to need it for example 9. Anyways, let's do Mn first. Mn is equal to square root y2. Yeah, let's do, well, I'll do x2. X2 minus x1, so b minus 0 squared plus 2a minus a squared, 2a minus a squared. And I get square root of b squared plus a squared is the length of Mn. That's one of them. Now let's do the length of N to P. NP. I'll keep this as the x2 and the y2. We'll make this one now the x1 and the y1. So x2 minus x1 is b minus 2b squared plus 2a minus a, 2a minus a squared. B minus 2b is negative b. Negative b squared is b squared. 2a minus a is a squared, is a squared. Well, I got Mn and Np are congruent. 2 more to go. Let's go PQ next. So PQ is equal to, notice the notation I'm using. No segment above it means measure of. We'll keep this as the x1, y1. We'll make this the x2, y2. So b minus 2b, square root b minus 2b squared plus 0 minus a squared, 0 minus a squared. B minus 2b is negative b squared is b squared plus negative a squared is a squared. And again, we have b squared plus a squared, square rooted. PQ is the same length. Last one, MQ. MQ. We made this the x2 and the y2. Let's make this, which actually goes back to the original x1, y1. Okay, so b minus 0, b minus 0 squared plus 0 minus a, 0 minus a squared. B minus 0 squared, b squared, minus a minus 0 minus a, negative a, squared, plus a squared, MQ, exact same length. All four of them are the same length. All four of them equal the square root of b squared plus a squared, square root of b squared plus a squared, square root of b squared plus a squared, square root of b squared plus a squared. MNPQ is a rhombus. Example 9. So we're going to be doing this proof here. It's a coordinate proof. We're going to prove that if two non-vertical lines are perpendicular, then the product of their slopes is -1. So this is something you've been told. You've been told that parallel lines have slopes that are equal and perpendicular lines have slopes that are negative reciprocals of each other, or if you multiply their slopes together, you get -1. Well, this is a proof that that has to be true. Okay, I've given you examples that perpendicular slopes, when you multiply them together, give you -1, but we haven't actually proved it. This is going to be an actual proof. I'm just going to follow the steps here, and this is going to take us through the proof, so we don't have to actually plan what we're going to be doing. We'll follow this diagram. Okay, so we have two non-vertical lines, L1 and L2. So here's L2, here's L1. They are non-vertical lines, so they're not parallel to the x or the y axes. Which coordinate point might be easiest to work with as a point of intersection? 0, 0. It's the easiest to work with. Okay. To work with the slope of a line, you need 2 points on that line. So we're going to take this intersection point as one of the points. And we're going to choose the other point, A, to be A comma B on line 1. What are the coordinates of point C? So A is A comma B. C is going to be A comma 0. Write that in both places. A comma 0 here, A comma 0. All right. Notice that angle 1 and angle 3 are both complements of angle 2. Why? All right. So angle 1 and angle 3, both complements of angle 2. Let's figure out why. We have a right angle symbol here. We said in the very beginning that L1 was perpendicular to L2. They're non-vertical lines. They're perpendicular to each other. Okay? So that's 90 degrees. The x-axis is going to be 180 degrees. So if this is 90, that means I have 90 left for angles 1 and angle 2 to add up to. Angle 1 and angle 2 are complementary. Because 1 plus 2 plus the 90 has to equal 180. Well, 2 and 3 are the acute angles in this right triangle. 2 and 3 have to be complementary. Okay. Well, if they're they're both complements to angle 2, we're going to figure out something about them. All right. So why? I just verbally told you why. I'm not going to actually write it out. I can give you the angle addition postulate, angle 1 plus angle B, we'll call this O, it is O, angle BOA plus angle 2 equals 180 degrees. Angle BOA is a right angle, it's 90 degrees. Subtract that, and you get the measure of angle 1 plus the measure of angle 2 equals 90. So angles 1 and angle 2 are complements. And then you can go angle 2 and 3 are the acute angles of a right triangle. And we have a theorem that tells us that the acute angles of our right triangles are complements. So angles 2 and 3 are complements. All right, this means that the two triangles pictured have congruent angles. Angle 1 and angle 3 are congruent to each other. The right angles are congruent to each other. Thus, so we have angle 1 is congruent to angle 3. We have a right angle here, and we have a right angle here. They're congruent to each other. All right angles are congruent. If we have any pair of congruent sides, then we're either going to have angle, angle, side, or angle, side, angle, or angle, angle, side. Angle, angle, side, angle, side, angle, or angle, angle, side. Any pair of congruent sides. So if I can get BO congruent to AO, or if I can get AC congruent to DC, or if I can get OC congruent to BD, then these two triangles are congruent by either angle, side, angle, or angle, angle, side. With that in mind, if we want these two triangles to be congruent, congruent triangles are desirable. So what would be a good choice for the coordinates of D? And I just said I want OD to be congruent to AC. What is the length of AC? AC is B units long. So what do we want for the length of OD? We want it to be B units long. B, comma, 0. B, comma, 0. Step 5. If you made the choice for D, so that triangle ACO and ODB are congruent, what must be the coordinates for B? Well, this is B. So this is B. I know it's B comma something. B comma something. What does the something have to be? Well, we need BD is going to be the same length as OC. We said that earlier. What is the length of OC? A units long. So what's the length of DB? A units long. Making coordinates for B, B, comma, A. Now we can complete the proof. We complete the proof that the product of the slopes is -1. Okay. How do we do that? Well, let's find the slopes and then multiply them together and see that we get -1. What is the slope of line? We'll do line 1 here. So the slope of L1 equals y2 minus y1 over x2 minus x1. We had to go through that whole process because we needed to know what the coordinates for B are going to be. If these are perpendicular to each other, we got the congruent triangles that prove that they're going to be perpendicular. Work forces this to be the same, and then we'll be able to work from that. So let's go y2 b minus 0, b minus 0, a minus 0. Oh, my mistakes. Small mistakes, but still a mistake. This isn't B, this is -B. Silly. Sorry about that. -B, -B. That'll make a difference in a minute. So that's got to change this one to a -B and this one to a -B. Sorry about that, because we're going to the left. The A is still positive because we're still going up. A went to the right here, A is now going up here. All right, B minus 0 over A minus 0 gives us a slope of B over A. Slope of L2, y2 minus y1 over x2 minus x1 equals. All right. It doesn't matter, but let's do, this is x2 and y2, so negative b minus negative b, negative b minus negative b over, oh goodness gracious, what am I doing? That was the slope from b to d. I want to do the slope from b to o. Negative b minus 0. Negative b minus 0 over a minus 0. A minus 0. Giving me, no, I did it backwards. y2 minus y1. Gotta be careful. That's why you gotta be careful. Details. A minus 0. A minus 0. A, paper's still on there, okay? A minus 0 over negative b minus 0, giving us a final slope of a over negative b. Much better now. And lead. Nope, still got some. All right. Now we want to actually find the product of these two. So b over a times negative a over b. Cancel, 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 cancel. Positive times negative. Negative 1. QED. Now, this is a proof because a coordinate proof. I just have to show the algebra. I've shown the algebra. I've shown that it equals negative 1. Product of two perpendicular lines is always going to be negative 1. Product of two non-vertical lines that are perpendicular will be negative 1. That's it. Thank you very much. Bye.